Hey, everybody. Thanks for joining. Really appreciate the chance to talk to you about some of the other side of the world for those of you in software about how our customers interact with our product. In the spirit of joy of learning, this is going to be a fun presentation. I know it's been a tough year for everybody in the last month, especially for some of you, has been really challenging. So we're just going to try to have a little fun for an hour. I'll kind of point out the parts that are serious, and the rest of it we're just trying to kind of get an idea of what's happening and how our customers are consuming our product. So the last time I gave this presentation about power and cooling in the real world was back in 2011. And so it had a old PowerPoint template. And for those of you who know me, you know I'm very particular about having just the right template and just the right fonts and all that sort of stuff. And so instead of doing that, I decided to go in the complete opposite approach, just to kind of have fun with it. So anyone who's joining later in the presentation is going to be very confused, but I'm calling this the MySpace approach. I'm a little bit too old to have gotten into MySpace, but it's amazing that it was the dominant social media only 12 years ago. It's just kind of an idea of how quickly things have changed. Anyway, I'm in technical marketing in Kevin and Andy Schutz's organization. My main focus right now for the last 4 or 5 years has been on Spitfire, both on the platform side. So that's in Amara Hellway's group's work on how we put all the systems together, and then as well as a focus on Silicon One. I've had a chance to work on the big routers for a long time. Back when I was in TAC in '95, I worked with this box that was the AGS Plus, and then since then 7000 and sort of everything we built in what was core and the XR product line, except for the access. So that's a little bit about me. Let's go ahead and just get started. The first thing to think about with regard to power and cooling in the real world is that there are lots of different environments that our equipment goes into, and none of them look like the labs that we use. On the top left is a picture of a web-scale data center. These are very highly optimized, very highly controlled. They build a model for their servers and their network, and then they replicate it at huge scale. These have the best power efficiency. These can have very good capabilities as far as how much power you can put into a rack. They've got the best cooling. They know what they're doing. They do it, and then it might be 3 or 4 years before they really have to touch much. The web scale data centers will be located around the countries, around the world. They're trying to be near enough to the clients to have good latency, but there also need to be somewhere that has a good cost for power. In the bottom right, this is something called a telco central office, and in the U.S., AT&T is the best known. Service providers have a different challenge, right? They need to be near their customers. They've developed, on copper lines to their customers, so they have to be near the customers. They can't just put their central offices next to, the power plant or the hydroelectric dam or wherever, country the power is cheaper. They need to be there. And then the next step is that the service providers need to have connections around the country, around the world, and to do that, they run fiber, and that fiber needs to get terminated, repeated, sent in different directions, etc. And in many parts of the world, those fibers run along train tracks. So if you need to connect a fiber between London and Italy, well, you don't get to put that data center wherever you want to. You actually have to put that along that fiber path. And so the fiber hut is where that comes up. So basically you have the fiber coming into a small location, you have power to it, and then you have some limited amount of equipment in there. One of the nice things that we're starting to do with some of our smaller systems, like the NCS 5500 1 and 2 rack unit boxes, and especially the 8200 Spitfire small boxes, is we're having the ability to put big routers in more and more small locations. The bottom left is the last one, which is a co-location facility. A co-location facility is sort of like a data center, but it's a lot less structured, and it's a chance for different people to come in and co-locate. They can put their equipment in the same building, and we'll talk about that in a bit more detail later. So the main thing here is people put our equipment in lots of different places. People use our equipment for lots of different things. If you are building out at the scale of Microsoft, which is a 50 megawatt data center every week, then every watt that you can save counts. If you're using our product to bring in 200,000 customers and selling them expensive business VPN services, then the services are more important than the power. So there's different needs in different parts of our customer base and different products. So this is some examples on the right of a web-scale data center. You can see a couple things here, right? First, these are lots and lots of servers. You see that it's very tightly organized, very repetitive. These servers will have a CPU, they'll have memory. The storage may be on the server, it may be somewhere else. All of these are going to have a copper cable going up to a top-of-rack switch. That top-of-rack switch is then going to have a fiber going into a leaf node in a cloth fabric. That's going to go into the spine of a cloth fabric. That's how it's going to connect to the other servers. And then some parts of that cloth fabric may also go out to other data centers or to the internet. These things are huge. The picture on the bottom left is actually the local nuclear power plant here in RTP. It generates just under a terawatt, and there are data centers now that consume almost that much power. Most of our customers like Google and Microsoft are building in that 50 megawatt range. It tends to be a good size to get efficiency, but what they want to do is they want to build multiple 50 megawatt data centers kind of in the same, maybe in the same metropolitan area, but it's better to have two 50 megawatt data centers, 40 miles apart or 40 kilometers apart, so that you have a little bit of geographic protection if some sort of emergency occurs. Okay, there is one that I'll show you some pictures of later in, I think it's in California, it's in Nevada. I think it's in Las Vegas or Reno, Nevada, that is planned to be an 800 megawatt data center. So almost the power of a traditional nuclear power plant. And if you talk about, looking at recent information from Microsoft, they're talking about building 50 to 100 of these every year. And we've been very successful in selling Spitfire to them, and so all of those, or many of those, will be built with our equipment for the network. Okay, so this is one of the serious slides. This is a slide that one of the senior engineers from Microsoft presented to it was actually a SerDes conference not too long ago, and he actually included a slide from Facebook in his slide. So the top right is Facebook, the rest is his content, or his message. But what I want to say here is that different customers care about power for different reasons. For some people, it's about just minimizing the power bill. For other people, it's not necessarily about minimizing the power bill. It's about having a fixed amount of power. So let's say, again, that 50 megawatt data center. If your capacity in that data center is 50 megawatts, every watt that you put into networking equipment is a watt that you can't put into servers, and the servers are how they make their money. And so what both of these charts are showing is there's a trend towards the network taking more of the total power, and that's a big problem for them. So they're looking at lots of different solutions, like how do we get the power for the optics down, because those have become very significant. How do we keep making the chips faster? But the problem that our largest web scale customers are trying to solve is to reduce the amount of power that's going into the network, or I think they would be happy just to keep it the same, but we can't continue this trend of the power percentage going up. Now, I did find some good news recently, which is saying that the work that the server vendors and that we're doing has helped keep the amount of power it's not going up as dramatically as you'd expect. You're talking about, over this period of time, 5 or 6 times the amount of commute, but the amount of the actual power is only going up a percent or two. So that said, consuming 1% of all the world's power is quite significant. So I want to take a step back and understand where the power comes from. Power is obviously created at, or is generated at power plants, and it needs to get from those power plants all the way to our CPUs, all the way to our optics, all the way to our networking ASICs. And as it does that, it's going to go through a range of different voltages and amperages, and sometimes it's going to be AC and sometimes it's going to be DC. But usually the beginning of the power distribution is going to be a 540 kilovolt AC. And the end of the power distribution is going to be 1 to 5 watts of DC. That's what the components in our routers run on. So how do we get it there? The first step, and you can kind of see from the labels on this picture, is that we start out at very high voltages. And the reason for that is the size of the copper cable that you need is proportional to the length of the cable as well as the amperage. And so by having very high voltage, you have lower amperage and your cables can be smaller. If you look at those cables going on those big overhead transmission lines, they're not that different in size from what you plug into the back of an ASR 9000. It's just that the amperage is, or the voltage is much higher, and that's allowing them to carry a lot more power. And so as you get closer and closer to the home, or as you get closer and closer to the data center or the fiber hut or the central office, the AC voltage is going to keep going down. And then eventually we're going to power the routers, or we're going to go into a facility either with 240 or 120 volts, if it was a residential or some type of facilities, or if it's a data center, it might be coming in the in the 400 volt range, the 400 volt range, and then they're taking the next steps. So one of the things that I want to kind of talk about a number of times in this presentation is that the power in a networking environment is far different than power in our home or in our Cisco labs. In our home, if a line goes down, well, we just lose power, or a plant goes down, we lose power, et cetera. We can't accept that for most applications of our equipment. And so there's lots of different things that have to be there. Traditionally, telcos will have batteries. So they're running 48 volt DC to their equipment. They're running DC through these batteries, and that's what's on the bottom left here. And so what's going to happen is if the power into the building fails, they're going to start powering things off of these batteries. And then while that's happening, the generators, that's in the bottom right, are going to power up. And then those generators usually have enough fuel for maybe a day or two to keep generating power. They can be refueled if needed, but hopefully the power will come up before then. When you hear about feed redundancy in the hardware, or AB feeds, what that's all about is having multiple power distribution paths inside the facility. For example, 2 different sets of banks, 2 different sets of breaker distribution fuse bays, different things that control the power, clean the power, switch over between the batteries or what's coming in from the transmission lines. Having 2 different sets of that, and so if the A fails, we can go and work off of the B. There's other stuff in here, obviously transformers. We're converting the voltage down from maybe 400 volts that came into the system to 220 volts that goes into the back of the router. If it's AC, we may need a rectifier to convert that to 48 volt DC. There's other things you can do. In the top right, that's actually a flywheel. So a different way of storing energy than battery is actually to do a flywheel. You can actually put them into a vacuum and let them go extremely fast. So there's different ways to store energy. It's not, batteries aren't your only option. But where this comes into play, and we'll see this again a few times, is that the power that's taken by our router is only a part of the power that's actually consumed by the facility. So if we need 1 watt, we're going to have some extra power that's going to be lost in those batteries. It's going to be lost in the transformers that happen along the way. It's going to be, it's going to be lost in the cooling, et cetera. So every watt that we save reflects more power than just 1 watt. So here's some other just pictures of things that are out there. So cooling is super critical. Getting the heat off of our ASICs, off of our optics, and then out of the building. Switch gear is how you cut over to the backup. This is challenging stuff. I think actually we recently had a customer fire that might have been around the switch gear or the UPS, in which one significant part of their data center burned down. So this stuff is carrying a lot of energy. The other thing our customers have to kind of think about when they optimize or try to optimize is the cables. So I've got some math to show that later on. But if you're running DC power into high power systems, you could easily take 1,000 pounds worth of copper just to get the system powered. And so that's the reason to go into high voltage as well. So for those of you who were around in 2005, 6, 7, MySpace timeframe, Dilbert was pretty big, so I just included him here for the reference. I think in this slide or in this cartoon, the data center is trying to get rid of all the people so it can do its own things anymore. Another fun slide, just to kind of understand what our equipment, where our equipment fits in the range here. On the far left, we have an Apple Watch. Again, this was 10 years ago, so I actually had a CPAC 100 gig optic. That's what 100 gig optics used to look like. As we get further up, you start to see toaster ovens and line cards, and the one that's showing up just before the routers is a pizza oven. So just think about the fact that we have these routers that are now generating 6, 7 times the power of a pizza oven worth of heat. So that's a huge challenge for these facilities to manage.
Hey, Lane, this power, am I audible?
I can hear you.
Okay, so this power, is that per annum or per week or per month? I mean, what's the metric?
So this is just taking this amount of power all the time. The costs we'll talk about will be about per kilowatt hour, but this is just the draw. And as a reference, a normal home takes about 2 kilowatts of power at any given time. And so this just kind of shows you how these compare.
So there. Is it per second?
So kilowatts is just the power. I think it has some time component built into it. But when we talk about the cost of power, we start talking about kilowatt hour.
Okay, yeah, I follow you. Okay, cool, thanks.
Sure. Okay, so there are a couple of different things that we want to think about with regard to cooling. The first idea is hot aisle, cold aisle. It's very important to prevent or limit your hot air from mixing with your cold air. You don't want the hot air coming back over the top of the rack and getting fed back into the system, because it'll just have a feedback loop and keep getting hotter and hotter. Air can come from the top or can come from the bottom. In our labs, I think we just treat it like a room. So even in our labs, it's just sort of like an air-conditioned facility. So it's not really coming from the top or the bottom. But if you're in a data center, it's going to be coming either down from the top, or it's going to be coming up from the tiles. And so there'll be holes in the tiles on the floor. I've got a picture of that in a minute. So the most efficient way to do things is to have really good air containment, either completely contained like this picture on the top right, or just relatively well contained. This picture, I think, in the bottom left is from that 800 megawatt center, and what they're doing is they just have cold air sort of coming in from the ceiling, but then they have a contained exhaust, and that exhaust is going up to the top of the building and then just kicked out into the desert from there. So they're not trying to recool that air, they're just getting rid of it. There are some cases in the routers in which this actually shows up. In general, almost all of our equipment takes, much of our equipment takes power takes air in the front and exhausted out in the back. So it's connecting, the fibers are on the cold aisle. Some of our access gear would like to go side to side. Some of the different systems will take it air in the bottom, go vertically and then out the back. The newer ones like the 5500 and 8000 just go straight through front to back. There is a special case that we manage on some of the smaller system, which is called reverse airflow or port side exhaust. This is something special case for the top of rack. Remember, before we saw that data center with all those servers, and then at the top of the rack, there's going to be one small one rack unit router. In that situation, we need the fiber side of the router or the copper cable side of the router and the copper cable side of the servers to be in the same place. So in that case, we actually have a different airflow than we do for everything else. So that's the role of port side exhaust, is to be able to connect correctly or efficiently to the servers. Okay, so here's a good example of cold aisle. I think you can't, and then you can see that every other aisle has the air conditioners and the other ones are hot. This doesn't look like great containment, but clearly it's not bad. I think this is one of my slides from 10 years ago, so things have progressed a lot since then. Our big customers have entire departments of PhDs who optimize their thermal environment. They do the same type of simulations on their rooms that we would do on our ASICs or on our platforms. And so here you can just sort of see two different models that are going on. Okay, this is an example of what a raised floor looks like. I don't know if any of our Cisco buildings have had this approach, but the idea of the raised floor is that you can run all of your cables underneath, which can get kind of messy. This is actually what we had in the first lab I worked with back in the TAC. And then what you can do is you can put these perforated tiles in front of your equipment, and depending on how much cooling or how much airflow equipment needs, you can put more or less tiles, and you can put tiles with different amounts of perforation, so you can control with much more granularity how much air is going into a specific place. I don't know if this is as common anymore, but this is the other approach.
So Leon, in SJ Building 20, we still have these tiles with perforations on them.
Okay, cool.
Yeah.
Okay, and again, this still is a 10-year-old slide, but you can get an idea of how well, which is the hot aisle, which is the cold aisle. Well, the blue one happens to be the cold aisle, right? So that's the front of all these systems. That's where their cables are coming out. And then on the right side, you see the hot aisle, and so you see just looks like three fans per server, and just stacks and stacks and stacks and stacks of servers. I'm not sure if they're getting that air out the bottom, but anyway, again, hot aisle, cold aisle is the kind of core concept there. This is a picture of that data center that Switch runs in, Reno, which is in Nevada. That's growing up to 815 megawatts. This is a huge data center. This is a co-location facility, so it's not, it's not like a Microsoft or Facebook where they control their own thing. It's where they're providing services to anyone who wants it, and we'll talk about the value of that in a second. Here you can see their thermal environment, and basically what they're doing is they were bringing in, cold air from the air conditioning overhead. They were containing the hot aisle, and then they just let all that heat go up into the into this roof, which is what you see in the bottom here, and then they just dump it outside. Other things in this picture, you can see some of the cooling units on the side, on the right, on the left. You see there's some generators. You see some I think some battery in here. So a whole bunch of different stuff going on. I've been hoping to visit this because it's really cool, and it's near Las Vegas too. Or they have another one near Las Vegas. Yeah.
Lane, is there ever a situation where you would use liquid? Oh, you just went to it. Never mind.
Yeah, so liquid cooling is really interesting. There's really two benefits you could get out of liquid cooling. The first is the ability to cool really hot ASICs. If we go back just 5 years to the first generation of Jericho, those chips were 75 watts. If we look at what we have now with the latest, Spitfire ASICs or with Leva ASICs, they can get up to 400 watts. That's starting to get very hard to cool. Maybe we can go to 500, but the heat sinks are now very, very, very large. So if you do liquid cooling, you can do you can do hotter chips. In addition, in some cases, you can do more efficiency, but you may not always get that. So in the bottom left here, this isn't a Cisco product. This is an example of cold plate. There's two main ways to use liquid. One is immersion. This is kind of common for servers and especially for Bitcoin mining. It doesn't work very well for routers because the fiber doesn't work well in an immersion environment. The other thing you can do is cold plate, in which you have something that attaches to the top of the ASIC or possibly the optics cage, and then you have a liquid which is pumped around. Like things like glycol are used. So in this case, you see that this is I'm assuming this is a server sled. It'll get plugged into the rack. It'll have a valve in which the cold liquid will come in where it's blue. It'll go through, it looks like these memories and the chips, not just the chips, and then go back out the hot. There are two different approaches that you could use for liquid. One is to actually have facility liquid, and this means that the facility is providing you with cold water. You're then exchanging your heat from the rack into that cold water, and so you don't have to have a lot of fans in the rack itself. That can be very efficient, but it also requires a big investment, and you need to make sure that all of your equipment can run that, or make sure that the majority of your equipment can run that way. The other approach is a rear door heat exchanger, or heat exchanger that's in a rack next to it, and that's sort of what we're seeing here. So the idea is that you're using the liquid inside the rack, and it's going into the servers, into the router. But you're still turning that back into hot air at the rack or near the rack. So it doesn't give you as much efficiency as chilled facility water, but it does give you the benefit of being able to handle hotter chips.
You see Cisco ever doing this?
I definitely do. We've been working on it for quite a while. There's a thermal lab I'm not sure if I think it's in 8, or it's in one of those buildings. So we've been doing testing with it for a number of years. There's all sorts of things we have to explore around what's the geometry inside that cold plate, what kind of liquids to use. So we've been looking into it. It's a big step. Getting facilities ready for it, getting the benefits. It's not a free lunch. There's power taken for to run those pumps and things like that. So we've done a lot with it. I'm not aware of any product shipping in the next couple of years on the router side, but we've developed a lot of expertise. Okay, so this is the serious slide. So this is not a MySpace slide, although it's kind of colorful. This is one that Rakesh put together. And what we're trying to talk about here is if we start on the left and we have an ASIC, it's going to take a certain amount of power for itself to move bits and things like that. But then as we go to the right, we're going to see all these different things that take power based on what happened in that ASIC. So as we're moving around just wire to wire over the PCB, some heat's lost from that. Some heat's lost, for quite a bit of heat's lost from the ASIC to itself. The point of load devices, these are the ones that do that final step of conversion. Remember when we started up at 500 kilovolts, we eventually come into the router at either 48 volt DC or usually 240 volt AC, sometimes a little higher voltages. We then have the power supplies convert that to either 12 volts or 54 volts, and then eventually these point of load devices convert it to 1 to 5 volts, whatever the optics or the ASICs need. And so in this case, those point of loads, they generate heat, so that's power that's been lost. Going over the back plane or the fabric, that's lost. The fans have to generate a little bit of their own heat. Power supplies generate heat. Now we kind of get outside of the rack. We've got the power cables losing some heat, PDU is basically what takes the power from the facility and makes it ready for for the router. Things like voltage conversion, maybe cleaning up the power. All these other things we kind of talked about earlier, they take power. The cooling systems take lots of power. Switches, et cetera. So what you see here is that there's a cumulative effect of every watt the ASIC takes quite a bit more power in the system. The PUE, or power usageness effectiveness, is the ratio of power used by the devices. So the stuff in the, for PUE, the thing in the dark blue on the left is kind of, that's where the number 1 starts. But then what's the ratio of that to power used by the, the fans and the batteries and the air conditioners and everything else? And so the PUE is the ratio of everything to what actually goes to the servers. Talk about that a bit more here. People have gotten really good at measuring PUE. This is actually something from yesterday that we pulled from a data center in Paris. And so what they're actually doing here is they're showing real-time PUE. 1.35 seems pretty good for a general data center. Data centers will be different based on where you are. If you're doing something in northern Sweden, then you have the opportunity to just take cold air from the outside, blow it around, and then kick it back out. If you're somewhere that's hotter, you're actually going to have to take the air that came out of your routers and cool it down and bring it back in again. So different environments will have different amounts of cooling needs. And in addition, different environments will have different types of air containment. If you go into an AT&T building that was built back in the 40s, it's not necessarily going to even have hot aisle, cold aisle. It might have some very rough containment with something that looks like shower curtains. So the PUE can range all the way from just over 1 for a absolutely modern Facebook data center up to something like 3. I wouldn't be surprised if a Cisco lab was in that 3 or higher range. Again, every watt we save in this case would be 1.36 watts for this customer, but for a lot of our traditional telco customers, it's much higher. So I just mentioned this briefly earlier, but I kind of wanted to highlight it again. The biggest equipment we use uses 2 AWGs called American wire gauge. It's how everything is scaled. The chart in the bottom right, when a customer asks me what kind of cabling do I need, well, the answer is always talk to your electrician, because different customers have different amounts of padding and margin they put in. But as a starting point, what you look at is what is your amperage and what is your distance. And for something that's more critical, you'd have a little bit different different tolerance. But you can see here, if we're talking about 30 amp links, which is what we usually have coming into our routers, running 30, 40 feet, you get into this 2 AWG and 4 AWG. And then you're talking about connecting 4 of those to each power supply, in some cases times 12 or 24 power supplies. You can very quickly get a lot of cable, and copper is very expensive, and it needs to be managed through these facilities. So this is one of the drivers to go to higher voltage. If we go into higher voltage into our systems, we can go with lower amps, which means the cables can be lighter. It also means that we have a little bit less power conversion that's having to be done before it comes to us. So next, let's talk about what is power cost. Sometimes when people start thinking about it, they just look up this chart from Wiki or something and says, well, what is power cost? And this is the chart of power costs in different parts of the world. And you'll see that it varies quite differently, quite significantly, through all the different countries that were shown here. And this is really what power cost for me, for my home. That's not really what power costs in the real world. The first step is that for a data center, they will have industrial scale power. One, power cost, and maybe it's 10 or 20% less. The reason for that is that one, they're buying in volume. Two, they're taking over some control over maybe cleaning up the power or doing some of the voltage changes themselves. So they're going to get a bit of a discount. But what else happens? There's a PUE. We talked about that before, but there was also building the facility, right? To build a data center costs a ton of money. So every kilowatt, right? So that's just enough to run a 1 rack unit router. Every kilowatt took $25,000 of facility to provide. So critical kilowatt means it's got those batteries, it's got that AB power, et cetera, et cetera. So it's not just that you're paying the power bill, it's you actually had to build that facility, and that CapEx is a significant part of running the data centers, because data centers are basically things that provide power and cooling to routers. Everything else is the fibers they cost some money, the servers cost some money, but it's the equipment and then power and cooling them. That's the whole game. The building, the walls, the floor, the lights, the offices, that's not a big deal. It's really about power and cooling. When working with actually it was Charter, who is one of the major cable companies in the U.S., sometimes they have a little different approach. We see that with our web scale providers, they're much more integrated in that the person who we're talking to about selling, we're selling the router to, knows all of the details and of what things cost. A lot of times with these more traditional customers, they're just paying somebody else, paying a different part of their company for the power. But a good a simplified way to look at that is Charter told us that for every power supply, and this is in the context of a CRS or an ASR 9000 or a Spitfire box, they need to pay about $10K per year per power supply. So that's everything for that supply, whether it's used at 100% or partly used, they need to pay that every year. And so we have systems with 12 power supplies, 24 power supplies. You can see that paying $250,000 a year for the power supplies is pretty significant. And this is actually related to a project that I've been working on, and that Sham Kumar and Aditya and Yash and Mani's team have been doing some great work on, is to avoid the over allocation. If the router is using 10 kilowatts, but XR thinks it needs 25 kilowatts, that means they need to put in many more power supplies and pay $10,000 a year for all those extra power supplies. So we've been doing a lot of work to reduce the allocation by taking into account more factors like which optics are present and things like that. So that's something that's just going to be shipping very soon. And again, I mentioned that there's different ways different ways that people pay things. Some it just may be per power supply. Some it's based on consumption. In co-location facilities, it might be based on a cost per rack with an allowance or metered power. There's a whole bunch of different ways to pay for it. A lot of the co-location facilities have only allocated about 4,000 watts per rack. So if you want to go in and put in an ASR 9000, you actually may need to buy 6 or 7 empty racks, meaning that you have to pay for them for the space that they're going to leave around your system because of the thermal footprint it has. We actually have seen pictures of places where we had CRSs in some co-location facilities, and they had a entire cage to themselves because they were sucking up the power and thermal budget for a huge area. And so this is what a cage looks like in a co-location facility. You'll notice that it's a lot less regular and a lot less structured than the big data centers that our web scale customers have. So there's two main values of co-location. One is that, let's say I want to have a few of my own servers on the internet, but I don't want to bring an ISP connection to my building or to my home. But I want to have a real server, not a cloud virtual server. I can go to Colo and say, hey, put these into one of your racks. I'll pay rent for them. This is just like a hotel. The second thing is you can actually buy cages and rooms. So in this case, this customer has bought this cage. It's got controlled entry. They can put their own stuff in there. If they were putting an 8818 with high power optics, they may need to put just one router in that whole cage and that consumes their whole budget, or they may have, a range of different things. The other big value for colo, and this is kind of the traditional value even before so much moved to the cloud, is that you can connect to other things. Traditionally, there would be something called a meet me room, and the idea is that each of these cages or each of these locations have fiber going to the meet me room, and then you can pay for connections between your cage and somebody else's cage. So imagine I'm a small ISP and I want to peer with 30 other providers. One option without a colo would be to run, to pay somebody to run a fiber from me to all these different SPs. Or I could put my equipment in the same SP as their colo, and then I can pay to connect to them just through this meet me room, or maybe direct fibers. This is one of the main things that the co-location facilities are selling, and you're going to pay for it. Just to get that fiber run through the facility, at the time we last talked to them, was $500 per month. Okay, so just to have that one fiber, right? That's a great very high margin, right? They run a fiber, they charge you $500 per month. Okay, the bottom right, that was the first video ever on YouTube, a little history there. All right, so how does our stuff stack up? Our routers are pretty good. If you kind of went traditionally through the high-end product line with the CRS and the ASR 9000, those are pretty high power. When we got to the NCS 5500, that was a big jump, big jump down in power. We get there with more ASIC integration, with single stage queuing versus two-stage queuing, so that alone, reduces a lot of memory operations. And then with the 8000, we take another big step, and then with the 8200, the single chip systems, we go, even lower. So I think I've got a slide coming up showing the progressions we've made over the last 10 or 12 years. The traditional equipment for Juniper isn't very good. Their MX was similar to ASR 9000 for a while, and I think the ASR 9000 has pulled ahead. The PTX was pretty similar to NCS 5500, and then their 400 gig generation, the power went incredibly high. It certainly looks like, so we know that Juniper has started coming out with, and we've known for a while that they're building, Jericho-based platforms. I'm not sure if it's mostly starting with J2C plus 7.2T chip, or if they're doing a lot on the 4.8T Jericho 2, but
J2.
J2, okay. So the stuff that they were building off the traditional Juniper silicon was getting really bad. In some cases, twice the power of what we had on Spitfire. So they're restarting some of their offerings based on Jericho, and in that case, they'll be the same as Arista. Huawei's big routers, and I know not everybody in this call does big routers, but that's kind of my reference. They're still building things like the CRS, so they're going to be very high. Another big trend to be aware of is that a huge amount of the power is shifting to the optics, and that actually provides a little context for one of the slides I want to show you about the trend. But if we went back 5 years, 10 years, the amount of power to the optics was a rounding error. We had, we had cards with lots of ASICs on them. We had the switch fabric ASICs. We had lots of CPUs, et cetera. And the optics might have been 10 watts. Now we have we have so many more optics, and they're taking a lot more power. Just going from the first generation of 5500 to the ZR Plus optics that are out there now, we've gone from 4 watts to 25 watts in the same QSFP size. So we're still putting 36 of those on a board. And so if you take the biggest box, we can now put 16 kilowatts of optics in an 8818. On the small end of the scale, if you took an 8201 with 32 by 400 ports, this is the Churchill that we're going to be shipping hopefully very soon. If you load that up with ZR Plus optics, you can see that the ASIC is now coming towards being the rounding error. The ASIC just takes a quarter of the power, and the optics are now taking 3/4 of the power. And the reason for that is that there's lots and lots of analog in there, so it doesn't benefit from Moore's law in the same way that the pure silicon does. So here's different kind of the trend over time. This is about halfway through my career at Cisco. So, but starting with CRS 10, back in those days, we actually used to advertise watts per gigabit per second, and at some point we had to change it to watts per 100 gigabit because the numbers were getting so small. But this is only maybe 10 years ago. We were at 220 watts per 100 gig. ASR 9000 was a little bit simpler because it didn't have all the infrastructure for multi-chassis. It started at 100 watts, and you can kind of see the trend that goes down all the way to the Churchill box that I just mentioned. And that 7 watts is a little bit deceiving because 3 of those watts are actually for, 3.5 of those watts are actually for the optics. If we were to do this again just based on the the silicon and fan and the non-optics power, almost everything else would still be about what it is, and then it would be half as much on the 8200. So the progression is incredible, and this is really what kind of maps into that press part of that press article I showed you, or the article I showed you before, that said compute has gone up 7-fold, but power isn't going up too much. Now, if you talk to Facebook, they're going to say it's going up way too much, but it's not. It's still doing pretty good. So here are actually some specifics that I put together for some of the team recently, just to show you, when I said that the power on the Juniper PTX was getting non-competitive. In this case, this is with their 400 gig. Our card is running between 650 and 750 watts. That's the Lancer Gibraltar, Q200 Gibraltar-based card, whereas their cards were running at 1600 to 1775 watts. So that's because they need more ASICs. Than we do. The ASICs an older processing node, and so you kind of see the range here. This is without optics, where we're actually half of what Juniper's doing. Arista has similar scale to us, has similar power to us, but they're using Jericho 2 without TCAMs, so we do have a bit more scale on Spitfire. On our 5500 offerings, we're pretty similar power to them. And then the bottom here, I kind of showed you what the power cost was for these routers. Okay. The place we do shine relative to Arista is in our small systems. Because the Jericho 2 is 4.8 terabits, if you need a 9 terabit system, you need to go to 2 of them back to back. And when you do that, the ability for our Pacific or Gibraltar 10.8T or 12.8T to do that with a single device creates a lot of differentiation. If you wanted to try to do something like that with the Juniper PTX 10003, the same thing that requires 1 chip on Spitfire requires 18 chips on Juniper. And the reason for that is that, this is about 2 years old, the reason for that is they had to have 16 NPUs, 16 1T NPUs, and 2 fabric chips. So they were getting all of those devices just to get to 16 terabits, whereas we're at 12.8 terabits with 1 device. And this is an example of why they're moving some of their portfolio over to Broadcom, is just because they weren't keeping up on their traditional legacy silicon. Okay, we're back where we started with the data center scale. This is from XKCD, and this is not that far off where things are going as far as the mentality of some of our web scale providers. So I left about 10 minutes for questions. Let's just open it up.
I got a quick one. Why is compute traditionally back to front? When all our networking hardware, it makes sense for it to be port side intake because cooling the optics has benefits, but compute seems to be mostly the opposite.
Yeah, I guess we could also answer why we're front, what we call front and they call front. I mean, one of the differences is that compute doesn't like to be likes to be serviced all from the same side. So that's a change. Whereas with networking equipment, usually we'll have the fibers on one side, and we may have something else, on the other side. Yeah, and traditionally, I think it's just legacy on both. You could certainly build servers, either. Well, I guess the fiber and the coaxial have to be the same on both of them. Yeah, I haven't thought it through, but I think it's just they put everything on one side.
The just tradition thing kind of, I guess, makes sense, and if they're just built that way, they're built to be serviced a particular way, and yeah. We run into problems, especially with those 400-watt ASICs. Trying to do back to front is extremely difficult because you're blowing air right over the hot ASIC right onto an optic. Not gonna like it.
Exactly, and it's a challenge in both ways. If you're blowing air over ZR plus optics, kilowatt of optics onto your ASIC, that's bad. If you're blowing air over the ASIC going to the optics, that's bad. The ASIC has the benefit of being more thermally tolerant. We can only run the optics up to 75 or 80 C, whereas the chip can run up to 110 or temporarily to 125 C. So that's important. There's actually a little short project I worked on about 3 weeks ago. Facebook came in and said, we've got this role. It's a very specific top of rack. It has 4 400 gig ports, 16 100 gig copper cables. It has port side exhaust, and if you can make certain thing work, we're probably going to buy 3,500 of them. So that's just kind of a scale, and that probably would have been just the starting point, and hopefully we'll get there. But this is actually a perfect example of a lot of the optimization we've done. And this is, again, a project that I'm working on with the team I mentioned earlier and Mark Guslin and a couple other folks. The way that everything has worked since the beginning of time is that we set the fan speed based on the ambient temperature. That is very simplistic, and especially now as we have these optics that might be 3 watts or might be 4 watts, they might be 25 watts. What we do now, and this is coming out in 7.3, 15.7, or actually I think it's coming out in 7.3 or 7.2. It's very, very recent. What we do now is imagine a function that takes 3 inputs. 1 is the ambient temperature, 2 is the optics that are present, and 3 is the line cards that are present. And based on that, we set the default fan speed. In some cases, that can have kilowatts of savings over what we would have done with the traditional approach. And then after that, we actually monitor the temperature of any high-powered optics and CPUs and flash drives and ASICs, and every device in the system gets to say how much fan it needs, and then we're going to run the fan at the highest common denominator. So rather than just doing a one-size-fits-all approach and saying, okay, it's 35 C, I need to run the fan at 80%. Well, if the chips aren't running at 100%, then the chips aren't generating as much power. Or if the optics are 2 kilometers rather than 40 kilometers, they're not generating as much power. So we actually have the ability to tune the fan speed in 1% increments in order to make the system run as low power as possible. And this is the kind of thing that's really resonated with customers like Microsoft, because when you scale up into their volumes, saving 100 watts here, saving a watt here and there is important, but this fan work can save hundreds and hundreds of watts in very normal situations.
Mm-hmm. Yeah, what we're probably kind of experiencing right now is a divergence in how we're going to have to build systems with 20-watt built for 20-watt optics versus systems built for 3.5-watt optics and below. Because it used to be a pretty narrow band of what an optic would take, right, between 2 and 5 watts, and
right.
Now the port can be between 2 and 23 watts.
Or zero.
Really challenging. Or zero. Yeah.
I mean, it's good copper cables take 0.
Right.
And of course, for those of you who are sort of on the software side, you may not be as exposed to the routed optical networking solution, or the hardware side of the routed optical networking solution. But one of the holy grails of service provider network for the longest time has been to combine the transmission equipment and the routers. And what that means is bringing long distance optics into the routers. We've tried this for a long time, but it's always required giving up ports. You may have a 36-port card for short-reach gray optics, but a 8-port card for longer reach optics. With the ZR Plus that we're talking about in the QSF PDD, we're getting those longer reach optics in the same form factor. The problem is that they're very hot, and we've set the expectation that we can run those at very high densities, and there's a lot of work underway to try to make that happen. Does anyone want to admit having a MySpace page?
I don't,
think it's,
but I do have a question.
okay. Sure.
So you mentioned that the hotter geographies have a higher PUE, so higher expenses on air conditioning. Do any of them? Can you use ground source heat pumps for cooling? And is it feasible? If so,
I'm not aware of it. I'm sure everything's been done in some volume. I'm not sure if it's been done. I'm not aware of it enough for it to be very common, but it might be. There's actually an interesting other approach to that, which is that you can construct cases in which you have a PUE below 1, and that's if you take your waste heat and use it to provide hot water that's useful. So maybe your the local town is getting hot water from your exhaust, and in that case you could kind of give yourself some credit. So there's definitely other ways to do it. It might be common, but I haven't run into it yet.
Sure.
I had a question on the fans. Why is it that we don't, if we have redundant fan trays, why don't we shut off one fan tray? Or sometimes they seem to be spinning faster than they have to, even at idle. So why can't we shut one off or bring it even down further to the even lower RPM than what they are idling at?
Sure. So two things there. The first one is that fan power is roughly cubic based on RPM. So it's better to have all the fans running slowly than to have one fan running very fast. Does that make sense? And this is why we really do everything we can to keep our fans getting up into the 70, 80, 90% range, because taking a fan from 80 to 90% doubles its power. Taking a fan from 30% to 40%, it's not a big deal. So we do everything we can to avoid getting into that range. I would say that the traditional approach we've had until most recently, and on everything except Spitfire, again, is just to sort of look at the ambient temperature and set the fan. So what that means is if the ASIC were generating 50 watts or the generator was generating 150 watts, we would have to set the fan as if it's 150 watts. So that traditional approach, we would be running the fans too high. The customers, the effort so far has been put on Spitfire. The customers who are buying Spitfire are probably more sensitive. So what we've been doing is addressing what you're talking about.
What about if you have redundant fan trays? Do they actually? I mean, you have two fan trays that are stacked on top of each other. If you shut one off, would that cause the other fan tray to need to work harder?
Yeah, it would.
Okay.
Yeah, and usually what would happen if one of those failed, the other one would just go to 100% without doing any math on how fast it needed to go.
As such, we don't have redundancy on the fan tray.
Excuse me? Yeah, actually, so let me back that up. So fan trays aren't really redundant. It's fans that are redundant. So if you pulled it out, the other one would go 100%. But yeah, it's usually just fans redundant. There's not a lot of moving parts on a fan tray itself that could fail. But fans. Yeah, it basically just holds the fans, and the fans can fail. And fan failure is not an on-off event. They tend to degrade, and there are different levels at which we start to consider them having failed. Thanks. Okay, looks like we're actually on time. So thanks everyone for your time. I really appreciate your attention, and let you get back to your regularly scheduled work.
Will you be sending out these slides, and was this recorded?
It was recorded, and as long as you promise not to use this template ever again, I'll be glad to send them out.
Yeah, no, I would like to go over this again. It's good information.
Okay, thanks a lot.
Yeah, all these slides and recording will be available on Joy of Learning portal. Len, please share this with me. Yeah.
Will do.
Wonderful session. Lot of good information. Any other question, guys? Otherwise, we are on time. Okay. Thank you very much, Len.
All right, thank you.
Great session. Thanks, Wayne.